So good afternoon. My name is Heiðar Ingvi Jónsson. I'm an assistant professor here at Reykjavik University and the head of the research council within the Department of Engineering. So it's my honor today to welcome you on behalf of Reykjavik University and the Department of Engineering to this PhD defense, where Hugo Cazaux will defend his thesis entitled Transformer-Based Time Series Forecasting for Company Returns with Multi-Provider ESG Data. His supervisor at Reykjavik University has been Professor Eyjólfur Ingi Ásgeirsson, and other members of his PhD committee have been Professor Hlynur Stefánsson, Dr. Ralph Rudd, Professor Sverrir Ólafsson, and Professor Marco Roberto. The thesis examiners are Professor Patrice Berlot, ex-Marseille University, and Professor Linda Ponta, University of Genoa. We are honored to have the examiners with us for this occasion. Welcome. The thesis defense will start with an open presentation from the candidate, lasting at most 45 minutes. Following the presentation, the audience will be invited to ask the candidate questions in connection with the presented studies and results. We will then have a short pause in the proceedings, at which time the general audience can leave the room if they so choose. The thesis committee and the thesis examiner will then hold an examination session with the students. After the examination, you are all invited to enjoy some refreshments, which will be served in Olympus, where we will have an opportunity to celebrate the candidates. So in conclusion of these formalities, I welcome the candidate Hugo Cazaux to the podium to give his presentation. Please.
Thank you very much. All right. So thank you very much for the introduction. My thesis, as mentioned, is called Transformer-Based Time Series Forecasting for Company Returns with Multi-Provider ESG Data. And my thesis committee, as mentioned, is shown here on this slide. So my main supervisor throughout this project was Dr. Eyjólfur Ingi Ásgeirsson. And in my committee, Dr. Hlynur Stefánsson, Dr. Ralph Rudd, Dr. Sverrir Ólafsson, and Dr. Marco Roberto. My examiners for the defense are Dr. Patrice Berlot from Aix-Marseille University and CNRS, and Dr. Linda Ponta from University of Genoa. I also want to take a minute to thank the funding without whom none of this would be possible. So I benefited from the Teacher Assistant Grant in 2022. The Sustainability and Institute Forum awarded me 2 grants, one project grant for the access of a database that we'll talk about a bit later, and a PhD support grant for a year, and the RU Research Fund that was awarded to me 2 years, for 2024 and 2025. Here you can see all the publications, the articles that we wrote for this thesis. So we have 6 articles, 4 of which have been published and 2 are in submissions. And we're going to talk about each of them during this presentation. Now that I've introduced the publication and the framing of the thesis, I want to start by introducing to you a few concepts that will be key and that will be talked about throughout the entire thesis. So let's start with ESG ratings. ESG ratings are metrics that were introduced in 2004 in order to measure the impact of companies of society. The goal is to model the non-financial aspect of company in order to get an idea of how a company can be sustainable environmentally, socially, or in governance. So these ratings were used originally for screening in the idea that you would not buy or sell from a given stocks depending on which ratings they have. And those ratings are subdivided in sub-ratings, usually 3, the environmental, social, and governance. And most providers also include a total score that brings together all 3. Like I said, the goal was to formalize the non-financial aspect of company. Another important concept that I want to introduce before we get into the meat of the thesis is time series prediction. So time series prediction is a very standard problem given historical observation of the past, which can be of a certain length and of a certain width, so a certain number of features. You want to predict the future time step, which will be either a single variate, so that will be time series prediction univariate, or multiple variates, so multivariate time series prediction. Finally, the third concept that I want to introduce is interpretability. Interpretability is this idea that when you have a model that is outputting prediction and you cannot explain why this model is outputting this prediction, it is not interpretable. People call it a black box, such as this box book by Christophe Molnar. And the idea is that if you have the input, the model, and the output, you should be able to trace back the reasoning and the process to which the model reached the conclusion it reached. And this is an extremely important topic in artificial intelligence, as we are adding more and more layers of AI in our society. For instance, in the legal system, in the health system, those are critical things. You need to be able to...
I want to fix the lights. Can I?
Go ahead.
Sorry for the interruption.
No worries.
Because I was looking at the Teams.
More light by the board.
Is it getting better?
Better?
It's better, yeah.
It's on the online meeting, it doesn't...
Yeah. Yeah. Okay. Thank you.
All right. Very good.
Sorry.
No worries. All right. So the research questions that we investigated during the thesis were the following. Do ESG rating carry signal for future financial performance? And how does that vary by sector and materiality? Materiality is a word used to describe the vulnerabilities for a given company at certain topics. Research question 2, how can advanced interpretable machine learning, including fine-tuning, improve time series forecasting? And finally, can built-in interpretability quantify the specific contribution of the ESG features? Those are the 3 research questions that we will be investigating throughout the thesis. All right, so following the order of the research question, the thing we wanted to start with was an initial study between ESG rating and financial performance. So we wrote this article and we published it in the Journal of Impact and ESG Investing. And the idea was to test if there was an annual, if there was a correlation between annual log returns, control annual log returns, and ESG ratings. For this article, our providers was Reuters, because we had an academic license at the university. And one of the first things we did in order to remove the influence of the market as much as possible from the returns of the company was to use a model called the Fama-French model. The idea is to remove the influence of the large trend of the market in order to get the return only from the company and to compare it in a fairer way, to correlate it in a fairer way to ESG ratings. And after controlling the return, we calculated the correlation. And this is the kind of figures that we got. So you can see that on this heat map, vertically, you have the different sectors of companies. The companies that we are looking at are S&P 500. And horizontally, you have the different score. So the ESG score, the larger score, and each pillar score or subrating. And you can see that, so the greener the points, the more there is correlation. And for instance, if you take the energy sector, it has 0.42 environmental correlation with the environmental pillar score. And you can see that this correlation really changes depending on which row or which column you're actually looking at. For instance, if you look at the technology sector, it has by far the lowest correlation, even though it's still positive. It has a lowest correlation that, for instance, the financial services that I can't reach, but that has much stronger correlation. And similarly, if you look vertically, you can see that the different pillars don't have the same correlation. The environmental pillar score has a much stronger overall correlation than the governance pillar score that has a weaker correlation. But another idea that we had was to not only split the companies per sector, but to split them by materiality. So like I mentioned, materiality are vulnerabilities that are recognized to be important for a given company. So for instance, you have air quality, but you have also water and wastewater management, employee health and safety. And depending on which company you're talking about, this company will be recognized as being material for certain of those issues. And we basically bucketed the company in those issues and tested the correlation. And you can see that we get a similar trend, but we get more individual numbers and more targeted numbers. And we gain another filter on how to see the correlation between control log returns, and ESG rating. All right, so at this point, we had seen that there was a correlation between annualized log returns and ESG ratings. And we've seen that it changed depending on the sector and depending on the materiality vulnerabilities that we're talking about. So what we wanted now is we had exploited correlation as a tool, but we wanted to use something that was more sophisticated and capable of capturing non-linear dependency and more complex dependencies in general. And for this, we turned to machine learning. And I want to start by introducing you to the machine learning pipeline. So the idea behind the machine learning pipeline is that you have multiple steps for training a fully trained model. And those are the steps that are being used in even the largest models that are coming out today. So the ChatGPTs, the cloud of the world. And the steps are the following. You start with the model conception. So the model conception is this idea that you are going to think about the architecture of your model and how you're going to stack your layers together and how you're going to process the data. And the data set processing is the part where you gather the data and you create some technical indicator that you might need in order to improve your downstream forecast. The pre-training is the step where you combine the model that you conceived and your data set into a pre-trained model. And this is the step that uses a lot of compute that you hear a lot about. This is the compression of the large knowledge that's within your data set using the model that you conceive. Finally, because you cannot release directly a model after pre-training, it would be very, for instance, in the LLM, there is this problem where it could be harmful to the public. Then you do something called fine-tuning, which is basically trying to align the model in order to potentially remove certain parts that are not not a necessity for the public, or that can be harmful. And once you've done all the steps, what you get is a fine-tuned model and a production-ready model. So those icons are going to follow us for the rest of this presentation at the bottom. And that way you can see how we introduce the same steps in this pipeline for time series prediction. And as we start with the model conception. And the model conception was a model that we considered in this paper, non-stationary transformer with time-to-lake embedding, which is submitted to transaction on artificial intelligence. And this paper is examining the use of destationary attention and of time-to-lake embedding on the inverted transformer, and how can we improve the forecast of the inverted transformer through those improvements. But you probably don't know what an inverted transformer is yet, so I will give you a bit of background literature in order to understand this. And in 2017, we had this bombshell paper called Attention is All You Need, which introduced the transformer. Very popular model, performed extremely well for anything related to text and translation, and became the standard for all the LLMs that you see today. It's the T in the ChatGPT, for instance. And it was adapted to a bunch of different applications, including time series prediction, and became the state of the art when this adaptation reached the research. Since this was the state of the art, people started improving directly on the transformer and make more specific adjustment for time series prediction regarding the transformer architecture. So here we have two examples. You have the informer, which is improving a long-standing problem with a long sequence. And you have the reformer, which is basically lowering the threshold for the attention calculation and making it more efficient. But in 2022, a surprising paper came out. This paper was called Are Transformer Effective for Time Series Forecasting? And it was introducing D-linear as the new state-of-the-art model. I really like this quote from the abstract, where they say that they used an embarrassingly simple linear model to verify their claim, meaning that they had shown that transformers were not performing above linear models in time series forecasting. Not only this, that was also an excellent news for the interpretability community, because the linear models are obviously much more interpretable than more complex transformer-based model. But this edge wouldn't last very long, and the transformer model became more performant quickly after. Specifically, two models shown here, patch TST and the iTransformer, the inverted transformer. So we're going to take a deeper look at the architecture of this model, and this is the one that we based our own model on. So the idea of the inverted transformer is that as opposed to the normal transformer, where you are going to tokenize your data set. Imagine a data set that is sorted in chronological order with rows of data with a certain number of features. When you tokenize this data on a normal transformer, you will tokenize alongside the row dimension, meaning each chronological entry is tokenized. The idea behind the inverted transformer is to shift this perspective and to tokenize alongside the feature axis, meaning you are tokenizing each feature instead of tokenizing a raw of data, which reduces greatly the number of tokens because usually you would have way less feature than data points in a data set. And it's much more efficient, turns out to be much more efficient for time series forecasting. And based on this, there is also a second order effect, which is that the attention, the multivariate attention, does no longer represent the interaction between the different entries of the data set. Rather, it represents the interaction between the different variables of the data set. So this is the architecture that we worked with and we developed. So there are two main additions from the original inverted transformer. There's the time-to-vec module and there is the d-stationary attention. So the time-to-vec module is basically a vector representation of time that captures the patterns of the dataset, while the variable projector network and the d-stationary attention is this idea that the relationship between variables is going to change over time, and you want to be able to scale and shift down the attention depending on how this variable or this relationship between variable is going to change. An example for this would be if you're predicting meteorological data, the relationship between the pressure and the humidity might not be the same in sunny weather or in cloudy weather. All right, so to test our model, we had 4 datasets. Those datasets are benchmark datasets: ETT, electricity, traffic, and weather. They have very different number of features, and they also represent very different things. For instance, ETT is a dataset where the task is to predict the oil temperature of an electrical transformer. The weather dataset is this where you have to predict the pressure of a meteorological station. Electricity is household electricity consumption. You have to predict one of the clients. Finally, traffic is the flow of the traffic acts in China. So it's different dataset where we are testing for different things with a very different number of features. And one of the perks of those datasets is that they're very comparable because they're used as benchmark for a lot of other models. So we get very comparable results right away. And those very comparable results are on the screen right now. So this table shows the 4 datasets that I just talked about. And here you have the prediction length. So this is how far forward we are predicting every time. And you can see that there are different models which are representing all the different state-of-the-art model. And they also tested for MSE and MAE. And so for instance, you can see the D-linear model I was talking about, or the patch CST. And our model, the NSI transformer, the furthest on the left, performs with state-of-the-art performance on ETT, ECL, and traffic, and in 2 prediction lengths on weather. So we were very satisfied with this result because we were beating out the original iTransformer method on most datasets, except for a couple of prediction length on weather. But we really wanted to get back this interpretability aspect that a model such as D-linear could have. And in order to do this, we could use the research that was done on transformer in order to extend it to the inverted transformer architecture. And the way we wanted by doing this, we wanted to gain more insights on the test dataset, but the downstream task was to get more insight on how ESG ratings can be used for prediction. And basically, we published this paper at IGCNN 2025 called Inverted Transformer Interpretability Beyond Attention Visualization. And to give you a bit of background, we used a technique that was originally designed for transformer called relevance maps, where the idea is to find pairwise relevancy between the tokens in order to get more insight on how the model is making a prediction. And this method is adaptable to the inverted framework, and that's the big point of the paper and how we wanted to get interpretability back into our model. So this is the result of this process in its most unfolded shape. You can see we have 2 layers. It's 2 encoder layers for a model, and from left to the right, the model is being more trained. So this is at the first epoch, epoch 5, epoch 10, and testing. And each cell in this heat map represents the relevance between two tokens. And remember, in the inverted framework, the tokens are features. So you can see that in the beginning, a lot of tokens are relevant between each other. And as the training progresses, we can see that less and less relationships are being put forward. For instance, here we only have very strong relationship here and here, or on the top right, whereas the most of the relationship have gone under 0.26. Yeah, 0.49 rather. And one of the problem with this representation is that it takes a lot of space. I mean, if you look at it, for instance, this is a data set with 7 features, and it can be really hard to read if you have 20 features or way more, like in other test data set. So what we came up with is a stack representation where we are stacking across the lines and across the layers. And this is what you get. You get the total relevance for a given prediction of each feature. So we make a prediction and then we get the relevance of each token. You can see, for instance, that here token 11 has basically no relevance, whereas token 12 is way more relevant for the given prediction. And this is also a good perk of an interpretability method, is that you can also use this as PCA to remove part of the data set that are not necessarily contributing too much to your prediction. Because you are capable to say, okay, I've trained my model on this and choose this data so I can remove the data and reduce some overhead in your computation. And we can see another example for a much larger data set with a lot of features. This is electricity, so 321 features would be unreadable in the unfolded shape. But if you look at the peak and at the data that is most relevant, so around here, the peak here, what's interesting is that you can compare it to the target. So here in blue, you have the target, and below you have client 112. Client 112 is the client with the most relevant peak, and you can see that the distribution is actually quite similar to the target. In fact, it's almost the same periodicity, and it's a bit shifted down compared to the distribution we are trying to predict. So, okay, so at this point, we had one backbone model that performed at state-of-the-art or near state-of-the-art level for time series prediction. Then we had shown that this stationary attention and time-to-vec embedding would improve the performance of the base inverted transformer. And also we had built the relevance map which can be applied to several inverted transformer architecture and can be used to see the relationship between variables. So it can be also used to see, like I've shown, to show which features are the most important for a prediction. All right, so at this point, we've done half of the model conception. The model conception, we needed a backbone, but we also need a fine-tuning strategy. And the fine-tuning strategy, we decided to use this model for it. We came up with this model called the centralized multi-agent reinforcement learning, which we published at ICMLA 2025. And the idea is basically how can one build a multi-agent model where you are changing the exploration and the exploitation phase in order to have a different kind of reinforcement learning. And so before I explain the inner working of the model, what I want to do is to explain why we settle on reinforcement learning as a strategy for fine-tuning. And for this, we need a bit of history and background, which is how fine-tuning has been traditionally done on large language models. One of the first way people started doing fine-tuning on large language model would be with human feedback. The idea is basically you take a prompt, you ask your model the answer to this prompt, and then you take a human operator and you add the answer to the human operator. The human operator writes a script corresponding to the answer of the prompt, and then the comparison of those two texts is back-propagated through the model to nudge it into something that is more acceptable and more in line with what the public might expect. However, this is, as you can expect, very, very time-consuming. Also, it's highly subjective as a method. So quickly, people went from this method to A/B testing. If you use regularly ChatGPT, you might have seen this kind of shape where the model is asking you which one do you prefer the most out of those two answers. And well, they're not doing this out of the kindness of their heart. It's in a way to nudge the model in a way that will suit more people. But you have to remember that you cannot release the model without any fine-tuning. So you still have to do this in-house, and the public cannot do this on their own at first. You cannot trial and error in the wild right away. So you need to do this in-house, and you have a human operator to do this in the company releasing the model. But then a new model came out, DeepSeek R1, in January 2025, which shown that their fine-tuning strategy was using mainly reinforcement, in fact, only reinforcement learning, and the only human operation were on the tuning on the environment, which is obviously much cheaper and has a much easier time to compute. Well, it's faster to execute, rather, not easier time to compute. And it's much cheaper because you're not paying any human besides the scientists that are tuning the environment. And also, this turns out to perform incredibly well, as DeepSeek R1 was a very bombshell model that really changed the way we were seeing LLM at this point. And so this is the architecture we decided to work on to basically use reinforcement learning. We wanted to implement reinforcement learning for fine-tuning time series predictors, and this is the architecture we wanted to use. So you have multiple sub-agents, and those sub-agents are each independent agent on the environment. They have a different, they can have a different reward function or the same reward function, but the idea is that in changing the reward function, you are favoring the exploration in a certain direction and trying to find novel strategies. Downstream, those sub-agents are feeding the recommended action to the super agent with the observation from the environment. And there is an attention module that is composing between those two data. But the idea is basically at the sub-agent level, you are trying to improve the exploration by introducing new reward functions. And at the super agent level, you are trying to improve the exploitation because you're using the strategies that were potentially discovered in mixed reward. And we try to basically make this model compete against two other state-of-the-art reinforcement learning model, namely PPO. So PPO, Proximal Policy Optimization, whose goal is basically to use an action network and a critic network. The action network takes an action, the critic network judges how good this action was. And GRPO, which is an article that was favored by the DeepSeek R1 paper, where you use the average of several action networks in order to get how good an action was. And so we compared the model. So thankfully, we have there's a tool called Mujoko, which is basically physical environment where you can compare different reinforcement learning models. Those are essentially control task. So when I say control task, I mean you have to make those creatures kind of go forward. So you have a two-legged creature. You have a knee and a foot trying to jump, and you have a humanoid. And you can see that our method actually performed really well on the benchmarks and on the reinforcement learning benchmark, beating out PPO and beating out GRPO. So we were very satisfied with those results within the control environment, but we had to use later on this model for fine-tuning. So we proposed multi-agent architecture, which was compatible with multiple reinforcement learning algorithms, because we used this algorithm alongside PPO, but this is also compatible with other reinforcement learning methods and algorithm. And this model can be used either with mixed reward, like I mentioned, to enhance the exploration phase and try to use different strategy, or it can be used to reduce the variance in training by having the same reward on each sub-agent. All right, so at this point, we are done with model consumption. We're going to move on to data set processing. And we have the method for the algorithm for backbone, and we have the data set, the fine-tuning strategy. So for our data sets, we needed financial fundamentals and technical indicators. Those were fairly easy to get. We got the financial fundamentals from Reuters, which we have an academic license for at the university, and we calculated the different technical indicators. And I mean, thankfully, Reuters was already a provider of ESG data, so we could get their ESG score from this. But we wanted to get multiple providers in order to have different ESG rating from different agencies, and we got those from Sustainalytics, thanks to the CIF, as I mentioned, and the SASB that we scrapped on their website. And the reason why we wanted multiple providers is, I think, something that is better illustrated than told. And I want you to think between those four companies, so Nissan, Japanese car manufacturer, Verizon, telecommunication company, Oracle infrastructure company, hardware infrastructure company, and Goodman Real Estate Company, which one do you believe is considered to be the most sustainable by a rating agency? Well, if you thought Nissan, Reuters would definitely agree with you and would rank Goodman as fourth and as the worst company in terms of ESG ratings. But if you ask Sustainalytics, then you get a completely different pictures. And all of a sudden, Nissan is the worst performer in terms of ESG ratings, and Verizon is the first one. And the reason why is because fundamentally there are discrepancies in methodology in the different ESG providers, which makes it that we need multiple ESG providers in order to hedge ourselves against things that the different providers might not catch. For instance, the Nissan difference in ratings. So you have the 6 in Sustainalytics, and then you have a 72 in Refinitiv. This is linked to the Carlos Ghosn scandal, and this is something that was not rated similarly in the Sustainalytics or in the Refinitiv framework. So, all right, at this point, we have our data set, we have the financial fundamentals, we've got technical indicators, and we have our 2 main ESG providers and the SASB index. So what we need to do now is we need to do the actual pre-training. We need to use our models on the data set that we've taken. So that's what pre-training is about, and that's what this paper is also about. This paper is in review at Journal of Sustainable Finance Investments, and it's basically investigating, can we use the NSI transformer to propose accurate prediction of company returns? And not only this, are ESG ratings going to improve our predictive power? And because we have the technology for it, can we use interpretability and interpret relevance maps to make sure that the ESG ratings are contributing, highlight the role of the financial and non-financial part of the data set. All right, so we had some initial results. We focused on three sectors, as you can see here. The reason why there is another line here is because we had to cut one outlier that had a very stark growth in the test data set and was blowing up the results. And we predicted on the day ahead, 7 days and 14 days, 2 weeks. And we compared once again with all the state-of-the-art method. And we were satisfied with the performance of the NSI transformer against the inverted transformer and patch TST. I mean, you can see that patch TST performed amazingly well, for instance, on those initial results. And so one of the problems that we had was that we wanted something that was as comparable as possible for the ESG rating for the different providers. So we had to basically create a cutoff in time, in the sense that Sustainalytics ratings only started in 2018, 1st of January, and Reuters started way back. Some of it was maybe back-made, but it started way back. So we had to do this first initial cut of the data to align and get the same amount of data points for each of for temporally, at least for both providers. And not only this, but we also had some stocks that were not covered in one and covered in the other. So we had to do the intersection of the stocks in order to be certain that we have the same companies for both providers. And once we had done this, we could run the test. So we used the NSI transformer on those data sets. And so you can see the finance, industrial, and the tech. And we used it with no ESG ratings, with only the Sustainalytics ratings, only the Reuters rating, and with both ratings. And what you can see is that the MSC, the mean squared error, slowly goes down as we are adding more and more ESG ratings. So if you compare from 0.322 to 0.255 when we add the Sustainalytics rating, you can also see that it goes down to 226 with 0.226 with the Reuters, but the lowest is the one where we use both ESG ratings. In fact, it's a complete sweep for the model that uses both ESG ratings as in MAE. It's a complete sweep here. You can also see that in MSC, for instance, we win out in the model with both ESG providers wins out in two domain here. And yeah, and in the industrial domain, the Reuters model was performing really well, especially in MSC, indicating that there was lower outliers in the dataset. All right. So those were results that were confirming the variable correlation that we saw in the initial study. And we were very happy with it, but we also wanted to use our interpretability in order to visualize how those predictions were getting better and enhanced. So for instance, we're comparing here the relevance maps for the prediction with no ESG on the left and with only Reuters and SASB on the right. And one phenomenon we spotted when we started doing these relevance maps was that a token that was often relevant, almost always relevant when we put no ESG, was the ticker. And the thing about the ticker is that this is a unique index that is designating a company. It tells a lot about the strategy of the model. Because if the ticker is really relevant, you can think that the model is checking this in order to fit a strategy afterward. If the ticker is Apple, then you're predicting something that will be related in test data set, in a train data set to Apple. But what you see is that once we added the ESG rating, and specifically once we added the SASB index, then the ticker becomes completely, it's token 14, the ticker becomes completely irrelevant to the benefit of the SASB index. And what's interesting is that this is a non-unique index. Multiple companies can be recognized with different vulnerabilities. And you can see it even better here. The relevance of the ticker is incredibly high, and it completely plummets in the second one with the relevance of the SASB skyrocketing. You can also see some traces of the relevance of the different ESG ratings. So here you have the Sustainalytics, and here you have the Reuters ESG ratings. You can see that some of the ESG ratings here are more relevant than the financial fundamentals, which are on the furthest left, basically the close price, the high price. And yeah, you can see also this even better here, where you have the total score. This is the total score for Sustainalytics, and the total score for Reuters that are performing the best, that are performing even better than a lot of the financial fundamentals or the technical indicator we calculated. All right, so at this point, we were satisfied with the accuracy of our prediction, the accuracy of predicting the control return, and we saw that was improved when the ESG data was added. Not only this, but the best performing model was the one who incorporated the maximum amount of extra financial data, and we used the relevance in order to really see and visualize how the strategy changed depending on which data we used. But this was the final step for pre-training. So at the end of this step, what we get is a backbone, and we get a backbone that we can still slightly improve. And this is where fine-tuning comes in. And fine-tuning for LLMs, you are trying to prevent harmful things. You are trying to prevent the user from asking dangerous questions. But in time series prediction, what you are really trying to do, you are trying to squeeze out the last bit of performance that you can and to reduce as much as possible. And the idea was, can we fine-tune pre-trained model to enhance time series predictors? And can we do this also with reinforcement learning? Because in LLMs, this is what's working. And we wrote this paper, which will be published as a book chapter, actually, in recent advances in deep learning in 2025, most likely. This is the methodology to fine-tune time series predictor using reinforcement learning. You have a data set, and this data set is going to be fed into the environment. The environment outputs an observation. The observation is really only a slice of the data set of a certain length that you determine. And this observation is fed into your backbone. So the backbone, recall, this is the model from your pre-training. And this model is going to give you a prediction. This prediction is equivalent to the action you were taking on the control task that I was showing earlier. So the hopper and this kind of things, it's equivalent. And based on this, you can calculate a reward. And based on this reward, you can use a reinforcement algorithm, create a loss, backpropagate, and improve your model. This is the way, the methodology to actually use time series prediction to fine-tune time series predictions. But one thing you have to consider is that there is a very a backbone model has been trained for a very long time, and you might not want to completely change the model by propagating the loss backward. So what you might want to do, what you definitely want to do, is to experiment with the frozen layers, meaning that you freeze certain level of parameters, threshold of parameters, in order to retain as much as possible of the high-level patterns. A good example of this is this table. So here you have 0%, 25%, 50%, and 75%. This is how frozen the model is, which what it really means is that the parameters are not changing and we're not propagating the gradient through it after 75%, for instance. And what we see is we tested the different algorithm, so PPO, CMAPO, our method, and GRPO for the fine tuning. And what we found is that usually freezing 50% of the model and using GRPO would yield the best results and would outperform the backbone. Remember, we're trying to squeeze out the last bit of performance. We're no longer in pre-training or we have usually, we're really trying to squeeze out what we can. So this is if you are fine-tuning on something you've already trained your model on. But there's another very common application of fine-tuning, which is transfer learning. And transfer learning is this idea that if you teach your model about a data set and you test it on another data set that's similar, then you should see some ability to predict. But this can be improved by fine-tuning. If you have a large model that it costed you a lot of compute to train in pre-training, you probably want to do a fine-tuning, which is cheaper, you're able to do some trial and error, try different algorithms in order to get more performance. And that's exactly what we did. So we trained models only on each sector, and then we fine-tuned them on each sector and compared to the baseline. And what we see is that eventually, for instance, in industrial, with the GRPO model, the GRPO reinforcement learning algorithm, we can beat out the baseline. For instance, here we beat out the baseline consistently with all three algorithms. And you can see that sometimes also the baseline just wins out, like in the financial here. And this is one of the perks of reinforcement learning. You can afford to go wrong, as opposed to pre-training where you need a lot of compute and you need a lot of GPUs, and it's going to cost you a lot of money to make an error. In fine-tuning, you can afford to try and change your parameters, and especially in algorithms that are sensitive to hyperparameters. So, all right, fine-tuning emerging as an essential post-supervised step, post-supervised training step. Not only this, but it's only going to get more important as we are scaling up time series predictor. If we make the largest the predictor, the more you're going to want to save the compute from it. And yeah, GRPO emerged as the best algorithm. So the same algorithm that was used for the DeepSeek R1 training. All right, so now it's time to answer our research questions. So do ESG ratings carry signal for future financial performance? And how does that vary by sector and materiality? Well, yes, ESG ratings are correlated to control log returns. And the sector and materiality do have an influence on which score is most correlated. And this was validated by the machine learning models that we developed. How can advanced and interpretable machine learning, including reinforcement learning fine-tuning, improve time series forecast? Well, we developed our own method, the NSI transformer, which perform at state-of-the-art and near state-of-the-art level on benchmark dataset. We also used CMAPO as an effective strategy for fine-tuning and for reinforcement learning. And finally, we developed fine-tuning for time series predictor. Can we use built-in interpretability to quantify the specific contribution of ESG features? Well, yes, we can. We can think about interpretability as we are implementing our pipeline in order to have this kind of relevance maps or this kind of techniques that are capable of visualizing as much as possible of what the model is doing. And the relevance maps itself were a tool to visualize and analyze the features and strategies enacted by the model. For instance, the contribution of the ESG rating that we have seen with the SASB index and with the different score contributing to the prediction. All right, so a bit of discussion before I conclude. I think ESG ratings are a valuable tool to us as a value company. I think the multitude of provider is a problem in the sense that there is big discrepancies in the different methodology, and this needs to be breached accordingly. I also think that the granularity of the data could be improved. A lot of the data relies on financial disclosure, which is not necessarily something that happens regularly enough to be exploited at the frequency that machine learning models would want. Time series prediction, I believe, are following the trend of LLMs in the sense that we are using the same model as LLMs in a lot of ways or slightly tweaked. So the same scaling laws should apply to time series predictor in the sense that the time series predictor are really in a second mover position where they can use the improvement in research made in transformer directly into the time series prediction. And a few of the things, for instance, that I think are going to be huge in that sense is the scaling. As time series predictor should be scaled from a singular dataset application to large universal forecasters that are fine-tuned down the road. And interpretability is a strong tool, determine model strategy. I mean, not only is it a strong tool to determine model strategy, but as AI is permeating more and more layers of our society, we need some sort of accountability as we are integrating AI in critical industries, namely the legal system, the health system. Those are industries where you need to tell people how and why a certain model is going to take this decision. So some of my future work, I would like to expand the dataset with more ESG providers to further complete the dataset, possibly add a longer date back for the dataset. Custom ratings, create custom ratings. I've seen this in different paper in the literature where people use custom ratings and they use, for instance, NLP to create from the news feed their own custom ratings. So you become the ESG providers, but you add your own subjectivity to it. Time series predictor, like I said, I think I really believe that this should be scaled up the way LLMs are being scaled up, and that this is the future in that domain. And also, some of the research that's been proven to be efficient in LLM should be integrated directly in time series predictor. For instance, synthetic data and chain of thoughts, which are two things that are being used quite a lot in the training of large language models. And directly integrates interpretability in pre-training and post-training. I mean, this is future work in the sense that it's a continuous work and something that I aspire to do in as much as in my models as much as possible, in order for it to be integrated in most critical industries and to have some sort of accountability if my model is making a prediction. Those are the references that I've used for this presentation. You can take a look here and here. And yeah, I think I'm thanking everyone for attending. Thanks to the examiner for making the trip to Iceland. And thank you everyone for listening. I will be taking any questions.
Yes, please, if there are any general questions from the audience. Now's the time.
Thank you for a very good talk. So when you're validating your time series, you calculate the MSE value.
Mm.
So you do this, so you train your model
Yeah.
and you compare it to the the test part of your time series.
Mm-hmm.
You only do this for, so my question is, do you try to train the model again with different, random initial,
well,
or is it just done for one?
for the benchmark dataset, we definitely train always on the same segment because you want it to be comparable, in the sense that the benchmark datasets are split in a way, they always split the same way for each of the models. So that way, everybody has the same trained data, everybody has the same validation data, everybody has the same test data. So we have actually comparable models. And I think for our own datasets, shuffling would be interesting. It's true that it could circumvent some of the outliers we had. One of the good example is, if I can go back a bit, is that, for instance, you see like this SMCI, supermicrochip computer. This is a company that skyrocketed in 2024, which was in my test dataset. And so the model would constantly underpredict, because it's really hard to predict that this model is going to, that this stock is going to do 10x, in a few months. And so shuffling would have definitely helped, but we didn't do any special shuffling. We're trying to keep the training in the segment that we define.
Thank you for a very good
Thank you.
talk. I appreciate you had a lot to cover, and then you went over a couple of things a little bit too fast for me. So maybe I missed it, so I apologize in advance. The interpretability, what I got was that there was feature relevance that you were mostly after.
Yeah.
Did you learn something more about the models, like the attention layers and how context matters?
Well, the thing is that because the way the attention is structured in the inverted transformer, the technique that we developed was mostly useful for feature relevance. Because, like I mentioned in the presentation, when we train the inverted transformer, the attention is between the different features. So feature relevance is the most obvious application for this, because especially in a time series predictor, you can, you can designate better which numbers are basing the prediction on. So yeah, this is what we mostly worked on, but it's obviously it's an open field, and interpretability as a whole can be defined in multiple ways and can have different levels. So I do think that for time series prediction, it's very important to have feature relevance, because you want to be able to know which part of the data set is useful and which part of the data set is less useful. And there are also tools to do this in statistics and these kind of things, but it's interesting to have it from the point of view of the model. But yeah, that's pretty much.
I can imagine that, like you could see some time horizons in the attention mark.
Yeah, some time horizon in the
whether there's a correlation between.
I think what would be interesting is you could make, for instance, a map and for a different length of prediction, and you would be able to compare the different length of prediction and see how this change and how different data is being valued at different prediction. Is that what you're talking about?
Yeah. Just a short question too. Like, so you did all your pre-training yourself, or is that how? What's the scale of your?
Yeah, I mean the scale of the data set was 253,000 data points. So it was manageable. You still need a remote GPU, but you can take the cheapest one from Lambdas, and they're the A10 and the A100, and they do the trick. So except for, like, for instance, the traffic dataset, 862 features. This has quite a lot of VRAM overhead. So usually you would need like a H10 or a H100 to actually run those kind of models.
Mm-hmm.
Yeah.
Thank you. That's it.
Other questions?
Maybe just
Yeah.
Are you predicting yearly returns? What kind of?
Yeah, it's a annualized control log return. It's a annualized control log return. So it's the return of the company annually and controlled to remove the impact of the market. So this with the FAMA French model right here. So we remove the impact of the market, and then we do the annualized return. That's what we're predicting.
But then isn't a mean square error of 0.5?
Well, it depends, because the if you're only predicting a single signal, yeah, that would be high, because you would be under predicting or over predicting. Okay, I think I expressed myself not well, because the return we are predicting is the return. Sorry. The return we're predicting in the model is daily and intraday data, like we shown here, because we have to change the granularity of the data. But the return we're predicting here is daily, and the return we were comparing the correlation with was annual. Little distinction I should have made during the presentation.
And how do you deal with the fact that ESG data are like I think every 6 months, and they're not the same.
That's a great question. We actually had a lot of reflection of this in the thesis, where we thought about multiple ways that we could basically tackle this problem. And we thought that the best way to tackle this problem was to do a forward fill, in the sense that you would basically fill the data, populate the ESG data as a signal that changes only yearly, in the sense that if you ask a provider, this is what they would give you in data. And we thought about, for instance, doing interpolation, but that would imply that there is a trend that is upward, whereas there is no reason why the trend would be upward. That certain decision will propel your ESG rating down or up, whether it's a scandal or a positive initiative. And there is no reason why we should do interpolation. We thought about also doing imputation, but there was risk of introducing compound error with the autocorrelation and then in the prediction. Yeah, so we tried a couple of methods in the thesis, and we settled on what we thought was the most interesting and the most relevant, given how the data is being published.
So
if there are no further questions at this stage, then I suggest we take a few minutes break, and then those that want to can keep them, and then we will continue with the examination session. And if anybody needs a toilet break, then that's the time.
Some water or whatever. Yeah, you have.
It's good water, don't worry, very nice.
You what? Yeah.
And the cross exam. Usually people leave in the question part.
Like in Switzerland.
Ah, really? Yeah.
Okay, so are we good to go? Everybody is online. That should be there.
Oh, I forgot to check out the team's question actually.
We're all set today.
That's a good point.
Okay, then, I think it's time to hand over to the examiners. So that you can, if you go first, then you, and you can sort of, you don't have to ask all of the questions at once. You can sort of switch between yourselves.
One question and at a time.
It's up to you. It's up to you. Yeah.
Yeah, okay, but
But I think one question at the time.
Yeah.
you have some.
I have yet
How many papers?
No. I answer by writing one and then I speak now.
Okay. So thank you, Mr. President. Yeah, first of all, I would like to thank you because you say thank you for coming, but it's a great pleasure for me, and I want to thank you. Thank you for inviting me in Iceland. It's a great pleasure because I'm going to combine work with pleasure. So the first thing I want to say is about the quality of your presentation because I think I'm very sure that it was not easy to talk about so many things you did.
Yeah, it was not easy. In my first rehearsing, I was over the hour mark, and I had to find a way to make the time. So I saw the time. It was like 44:27. I'm like, okay, we're not over it. It's good, but there's a lot of concepts. It's really hard to get into. A lot of them I really want to, I'm passionate enough about that I really want to show them. So it's I wanted to show basically everything we've done throughout the thesis, and I think the presentation reflects this very much.
I was wondering what would be your strategy for the defense, but yeah, I really wanted to congratulate you because you presented complex, the concept very clearly, a lot of results. And moreover, the defense is the presentation is complementary to the dissertation.
Yeah.
So
I think so.
new illustrations and new way of so I really appreciate it.
Yeah.
So I don't think it's necessary that because there is no public behind me, but that I repeat to what I wrote in my report. So yeah, I have some questions. So you try. I saw the change log you
I sent you. Yeah.
So thank you for that because you took into account every comment I sent to you.
Yeah.
But I still have many questions, but I have some dozens of questions. But I haven't decided yet what maybe I have some general question because they are the most
Yeah, absolutely.
for me.
Absolutely.
Now. Maybe the first one is about the applicability of your proposal to other kind of criterion of objectives of non-financial aspects that a company can. I think about, for example, I think about innovation.
Yeah.
So what do you think about using your proposal to
Yeah. Okay. So my main the main thing that I want, like I mentioned, specifically for so there are multiple pendant to this answer, but I will go through each of them. For the ESG results, in the sense that I founding that the ESG results are important to the prediction and to the predictive power. I think the simple application is that you should take those into account when whether you are a practitioner or this kind of things, when you are making a prediction, which is something that's being done, but could be probably done more. Not that I am a practitioner myself, but also that try to incentivize people to use this signal as something worthwhile to make a prediction. For the time series aspect of the thesis, what I really want is to scale up the like I said, the time series predictor. I think that's the way that time series predictor should go, in the sense that what we've seen, in LLMs, for instance, there is this result where they taught an English to an LLM and zero code, and it performed far worse at grammar. And then you realize that when you are teaching, an LLM with code, well, it performed better at grammar because there is all those border effects and transfer learning effect that are improving the performance overall of the language of the model. And I think that's really similar in time series prediction. I think that's a thing that should exist. I mean, the same models are being used more or less, but with some stretches. The same model are being used, and they should have the same laws. They should respect the same laws. And I think that's one of the things that I really want to work on. One problem with this, and I will point out a limitation of my own work and a limitation of a lot of the work in time series prediction in general, is that very often when you are doing time series prediction, you're assuming a few things that never hold up for multiple data sets. First thing is the input size, the sequence of the input size. That's somewhat of a problem because you can always pat or truncate depending if your input is too long for multiple data sets. But there is also the number of features. The number of features can change depending on your data set, and then your network, fully trained network, can become unusable. And there is also the size of your inputs. That's the least worst problem because you can always truncate. If you need 7 or if you need day after and you get 7, then you just take the first value. That's not really a problem. The real problem is the entry and the features. And there are some models that are trying to tackle this problem in order to scale it up and in order to use multiple data sets. But often they rely on projection. They will do like an embedding or a projection of a data set that has 120 features into 10 features. And I feel like you lose so much information doing this. So one of the areas where it needs to be improved is this capacity to be able to accept multiple input length and input width in order to really scale up and be able to, for instance, imagine we could train on the models such as like the ETT model that I presented, traffic and weather. Imagine we could train a model on all those data sets. Maybe we could see a better performance, but it's impossible for now because they don't have the same number of features, even if you can set the same prediction length. So yeah, that's the main thing. And the way my research inscribes into it is that we modified, a foundational model, which is inverted transformer. There are modifications that can be found that will not only improve the forecasting, but also improve the extensibility of the model. And I think that's really the way that you will go. And fine-tuning will become way more important once this is true, because this fine-tuning doesn't have to change. The fine-tuning already works if you have. It doesn't matter the input size of your fine-tuning, really. If you can always tweak the environment in order to make it work. So the fine-tuning, I think, will only become more and more important.
Yeah. Okay. Yeah, I have a question also about the nature of the. I don't know. I fully remember what I was in my report about the causal aspect of the data, but whatever. The fact is that you combine financial data that are related to present time with other data, the rating, and you only have this data once a year or what, but it doesn't matter. The time doesn't matter. But these data are about will change the future.
Yeah.
So you thought about using forward field and so on.
Yeah.
But what about dealing the usage of the data?
Dealing the usage. So use the data from the past year, for instance.
Yeah, but only for ESG.
For ESG ratings.
Because ESG will influence
the future.
So the time.
Yeah, that's definitely an interesting.
I don't know.
Yeah, I think that's an interesting idea. I think it would be definitely worth exploring to use the past signal in the sense that you could imagine, for instance, a company being tanked in their ESG ratings, and all of a sudden funds are no longer buying of that stocks, and then the stock plummets.
Yeah.
So I think that's definitely a relevant approach. I think there were no, because I looked in the literature of what people do to tackle this kind of problem of the granularity.
But in the computer science field, or the you?
No, I looked in the ESG ratings field mostly. I looked in the ESG ratings what people did for granularity, and I saw a couple of different approaches. I saw some imputation, for instance, that was being done, and I don't know. I wanted to do something that was also realistic, but be compared to what you would get. Because, for instance, like I said, if you do linear interpolation, you're kind of supposing that you know the next data point in order to make your interpolation, which I think is not realistic because it would mean that the rating is trending up, where it's just spiking in one way or the other. But I like your idea of really it would be a backward fill. If it's a backward fill as opposed to a forward fill. Yeah, that could work. Yeah. I didn't try it, but I think that could be warranted. That could work.
So you were inspired by NLP approaches, but a lot of NLP tasks can be seen as time series prediction. For example, sentiment analysis or emotional analysis.
Okay.
When you are watching movies, your feelings are changing or changing and so on. But have you heard about using high transformer for NLP tasks?
I have not heard about inverted transform for NLP task. I've not heard about it. I've not heard about. I don't know how this would apply and how this would work, but why not?
Because I must say that it was by testing, by applying your proposal to evidence.
I think
also for reinforcement learning, because what you mean, what you made greenwashing and
discrepancies, of course.
Maybe there's just like fake news or bad faith when you comment a film, a movie, or the object.
I mean the discrepancies. So the discrepancies and greenwashing and this kind of things. That's one of the reasons why we had to get more providers inside of the data set in order to cover this. But for the application of the models to NLP, I think the classic application of reinforcement learning now is the fine-tuning. And the fine-tuning, I think that's you can do this on most NLP model, especially if you formulate your task, like you said, of NLP as time series prediction. If you if you have a finite alphabet or this kind of things, you can treat this as a time series. There are many ways of interpreting the task in a way, because really what the inverted transformer or any kind of transformer is doing is like interpreting the task that was based for NLP, which was the the tokenizer and this kind of things in the 2017 paper, into something that works for numbers. And that's the idea behind the inverted transformer, is that you're not embedding like this rows, because that doesn't make sense. It's not an alphabet.
I was thinking about the polarity and the sentiment of the. Okay, maybe we talk. May I last question? Maybe. I have a question about what you in the future work. You talk about completing the data set, but what kind of you mean adding more ESG data or to complete the data set with other kind of data?
I think the data set is a very open question, in the sense that we could explore more possibilities with interpretability, these kind of things, if we had more providers. I mean, for one of the providers that we didn't have, Brobeco-Sam, for instance, that was in the study that I cited to show the discrepancies. I didn't have these providers, but there are so many providers. There is Moody, or we could get like those kind of the other providers, but also it's, for instance, to get the Rutgers data set, it was fairly easy because we had an academic license, but the Sustainalytics data set was, we had to go through a license, we had to go through the process of applying to get a grant, and we got the grant and we got the data set, but it's a process that was hard enough to the point that I didn't want to wait eternally on multiple providers. So we scrapped the SCSB website, for instance, to get their own, the materiality issue properly. Yeah. So that.
But there are still ESG ratings or ESG metrics. But do you think about other?
All the kind of data. Yeah. I mean, we could add so much more data. I mean, there is stuff like interest rates that we could add. There is just general data.
Or information.
Information. Yeah. Of course. Yeah.
Okay.
Yeah, information. I think the what I mean in custom rating exogenous data is kind of this, is just you can add any kind of information to and you can try and see if it makes your model better, and there's a cost to adding. Sorry, you were gonna say something.
No.
Okay. So there is a cost to adding more data up to a certain point, But that's where interpretability shines. Is that if there is a cost to adding more data, then what you do is you do a training. You downscale your data set, for instance, and you make a training. You just train your model, and then you can see okay, like this data I just added is completely irrelevant. It's useless for my prediction. All right. I'm not using it anymore, and then I'm going to add something that maybe is going to, and you get iterates on your data set like this. This is where interpretability really shines, I think, in time series prediction, is the tuning and the capacity to iterate on what you were doing.
About the data set, so I understood that your data set is based on private.
Yeah.
Data. So you can't distribute it. I understand that.
Yeah.
But anyway, you can make it findable, accessible.
I can
Reusable, etc. So the fair principle.
I know. Findable, acceptable.
I wanted to.
I do agree, and I want to make it as shareable as possible. One thing I can do is that if you have a license, I can give the exact script to get the exact same data in the same setup. I can also make different data tests. I can make truncated data, anonymized data. I'm not sure if I'm breaking a license doing this, but I know they're quite finicky. Also, it's two different organisms that don't talk to each other. So it's hard for me to find, a compromise where I can say, all right, I will be, releasing the data but I am obviously not opposed to share the data as much as possible. It's I'm more contractually obliged to, give as much as I can without breaking what I signed.
I think that you can make some kind of publicity about one. Yeah, maybe writing with data paper and so on, because the process to talk about it is very important.
Yeah, definitely. It is like a whole topic in itself.
Absolutely. Thank you for your answer. Sorry.
I thank you for your questions. Yes.
Professor, for the invitation to be part of this committee, an honor, and also to have the opportunity to read this interesting thesis. And according to me, the main contribution of the thesis is this mix to mix this
Absolutely.
of data. One prices that are returns, of course, that are very standardized, let's say,
Of course,
collected in database, and the other side, the rating that are instead the opposite in some sense.
Scattered and
So, according to me, this is an important part, and also the contribution in this way, the thesis is an important contribution to the field of finance.
Yeah.
Saying that, I have some questions.
Yeah.
The first one is quite general. You said in the thesis that the complexity of real financial systems and the nonlinear dynamics limit the ability to use correlation, simple correlation analysis.
Yeah.
And so you decide to go to machine learning.
Yeah.
And my question is, if you can elaborate a little bit more on why you choose this methodology and what are the main advantages of having this methodology?
Yeah, of course. Well, first of all, so the first thing is that when you study just correlation, what you get is a trend. You get an idea and a strength for how much two variables are varying separately, but you don't get a picture that is a little broader. And the reason why I wanted to work on machine learning is because I think this is a tool that is implemented more and more in the current financial system and in the current funds that are acting on the market. And I believe because of this, that in the academia, we should try to replicate as much as possible what's being done in private companies. And although I know that the models that are being used in private companies are not directly the same as what I'm proposing in the thesis, I'm trying to create something that is as close as possible as you could find if you went to some fund and they had their own predictive model, which I think is to the benefit of ESG ratings and to the benefit of the financial system as a whole. And yeah, so that was the approach that seemed to me the most interesting. And besides this, there is also my personal interest. I'm very interested in machine learning and artificial intelligence. And, I'm a software engineer of formation, so that's my main, one of the main thing I was really interested in. Yeah, absolutely.
The data,
Yeah.
That, you use two sources, the different granularity, the lack of quality.
No.
So you use the forward field strategy instead of extrapolation or regression, I said. But and I understood that probably it was the best strategy. But
there's a balance.
The question is, what are the potential disadvantages that this?
Disadvantage. Oh yeah, I mean one of the disadvantage of this is that you don't get a signal that shifts as much, because if you were to plot what the ESG rating looks like, you would get a long line, a step, a long line, a step. That's what it looks like in the data set. So obviously this is not a signal that is going to have a very minute change. If we could change if we could have ESG ratings that were changing, for instance, daily, same as the high price, the low price, or these kind of things, would probably enhance the prediction further, I hope. But the reality is that we know that sustainable initiatives do not take a day. So it's very unrealistic, I think, to have the rating change daily. But maybe monthly could be something. It would be a little granular, and I think it would give more information. Right now, you treat the signal more as something that shifts as it's per company, so it's not something that's shared to multiple company, but it's something that shifts slowly. And there are many kind of data that are very influential. I mean, for instance, I was talking about interest rate earlier. Interest rate doesn't change very quickly, but it's extremely important. And just the fact that the frequency is low doesn't take away from the importance of it, I think. But obviously, it would be better if there was a change that was a little more representative of what the companies are doing. But there is a problem with disclosure, and I'll mention that. Yeah.
EMA, PPO.
Yeah.
Work.
Mhm.
Novel. I was wondering, you have a sub-agent.
Yeah.
You have the and one super agent.
Yeah.
Now, my question is, what are if it is possible, maybe to create a hierarchy, so you have agents.
You mean layer it more?
Yeah.
Yeah. I think that's possible. Yeah.
Because maybe it requires too much time, or I don't know, the performance in general.
Yeah. I mean,
and
yeah.
also the efficiency of
of the model. I mean, okay. So in terms of efficiency, you can layer. It would work in the architecture. You could layer the model. You would have to think about how you would connect it, because either you connect all the subagent to one subagent and then to the superagent, or you just do something linear, but that would be, so I'm not sure how you would try. You would have to investigate to try and see how it works, or how it works best, at least. The trade-offs, yes, definitely computational overhead. I think the computational overhead would get larger. There is also a bit of would be harder to kind of manage, that many subagents. But I also think that, for instance, one of the reason why this model performed well was the attention model that we placed at the end, that was trying to split between how the model, how different subagents were doing. And one of the extensions that I wanted to make for this particular model was that right now it's splitting between the suggestion of the subagents as a whole and the environment. But I would like to split between each subagents and the observation. That would make more sense and probably have a better performance. And in this, I think you could layer the model way more in this way, because you would segment more with the attention, the different subagents. I think it would be a little easier for the model, because the more subagents you're putting, the more you increase the observation space of your superagent, because you're increasing the action space of the subagent. So yeah. There's probably a trade-off there. So yeah, but it has to be investigated more than yeah. Yeah. Yeah.
Performance
Improves, the MSc and ME.
But my question is why it is not a source of noise, because sometimes the ratings are different, as you show.
Yeah.
So why this different rate?
Yeah. I think that's a good question. I actually, what I think, I haven't thought about it that way, but what I think happens most is that because we are testing on entire sector, there is a smoothing out of the noise that can happen between the two types of data. In the thesis, I talk about the training strategy that we used. I didn't have time to talk about it here, but we use this walk forward strategy to train on multiple stocks, because we need to find a way to make multiple stocks work together. And yeah, I think that on the bigger scale, even if the providers have discrepancies and the providers might disagree, I think there will be some big themes that hopefully they will rejoice, and some of the discrepancies are going to be smoothed out by the number. And if we had even more providers, the smoothing out would be even more efficient, I think. No. Yeah. Mm. Yes. Yeah.
My question is what computational and modeling challenges does this entail, and how can your current findings of scalability and interpretability can address these challenges?
Yeah.
And if the generative AI can
Yeah.
help in this, and then maybe other data that you can think is the standard, the classical data, standardized data of that can be found in the balance sheet of firms. So the investment in R&D can be a proxy of innovation,
Definitely.
patents.
My take on this is that on the scaling up is that I believe, at least, that given what we've seen with the large language models and the models that are in production currently, if we take a time series predictor and we manage to find a way to train it on very different set of data, which also include financial data, we should see increased performance on the overall picture because of the border and transfer effect. So the challenge is obviously that you want to scale this up as possible by having a lot of data. So there is a challenge with the data pipe that you have to, the data storage, for instance, but some of the ways that you can tackle the data storage problems or the data scarcity problem, synthetic data, which in time series prediction, it's actually very simple. You just have to use different distributions. You take a distribution and then all of a sudden you're only producing on RAM, you're not producing on storage. And that's saving a huge amount of compute. And you can see that in the most modern model, some of them have 40% of synthetic data. It's incredible, like how much they're scaling up the synthetic data. So I think that's one of the things where we can circumvent a bit of computing. But I mean, I'm not gonna, there is definitely a computing challenge, and it's something that you can play around a bit in the sense that you can always, rent remote GPUs to train, but to get to the scale of the biggest companies is really hard. Thankfully, the new results, which I like a lot, is people are using distillation more and more and making smaller and smaller model in the end. I've seen that there is some scaling laws that are being studied where over 7 billion parameters, the scaling tend to smooth out. So I'm hoping that it won't get too much ahead, and that we'll focus more on distillation so I can, afford to make a model that size without breaking the bank. But yeah, I mean, the computation is a big challenge. And if you can bake some sort of, mitigation, you can really shine through. A good example, for instance, is DeepSeek R1. DeepSeek R1 is a story of scarcity. The reason why they use reinforcement learning is not even because they wanted to do it or this kind of, well, I'm sure they wanted to do it to a certain degree, but it's mostly because this is a side project of an hedge fund in China, and they didn't have the money to hire enough human operators to do traditional human feedback. So they use this technology in that way. And I think in scarcity is where you are the most ingenious to make the better, better models and better improvements. So yeah. Yeah. Yes.
Five instead maybe of three.
Of the three, yeah.
And also which kind of data you use to make the linear regression.
To make the linear regression, yeah, of course. So first of all, we used the Fama French model. The reason why we used the 5 factors is just recency. I saw the paper and I thought, yeah, that's sounded like the most, the most. I saw there is more parameters you're trying to remove more from the market. That sounds like something I'm looking for. And for the way we did the regression, the parameters for the model, actually, if you go to the website of the author of the paper, I remember it's well, it's Canet and well, it's Fama in French. If you go to their website, you can get the parameters daily for every single company. You can get basically the parameters, and you can run the regression based on those parameters. They just keep updating it, and you can get the data from them. So yeah, that's. I just scraped their data and did the regression myself after. So yeah.
Would you like to continue? More questions at this point, or perhaps Eyjólfur or Hlynur have any questions?
Maybe one quick question. We've already had
Tell me.
many excellent questions. Thank you so much.
Tell me.
Yeah. Like, okay, you're looking into returns or changes in stock prices. What about like the relationship between like the ESG and the risk? Do you think there's like a...
Oh yeah, and the volatility, for instance.
Yeah, exactly.
Yeah.
I mean, yeah.
There was a point where I wanted to explore this, the relationship between the risk and the volatility, but I didn't feel like I had the enough financial background to really put through something that would satisfy a financial audience. And I feel like my reach was more about the method on how to improve the prediction and see how the tools we can use to see how the data relate to each other. But yeah, there is definitely some interesting ideas here. I know there is some work done with copulas and those kind of mathematical objects, but I saw it and I thought, yeah, maybe in another.
Yeah.
Maybe if I do not know, I'm not.
Good answer. Thank you so much. That's it for me.
Just one sort of curiosity, because you mentioned your chain of thoughts. Which falls under the second bullet.
Yeah.
Have you given any thought sort of how you would
Compared to
chain of thoughts going in this?
Yeah, I thought about it actually. My idea was that it would be kind of similar to what you do in fine tuning, sort of like a mini fine tuning, in the sense that because there is no real reflection, especially in time series prediction. Like if you look at the chain of thought model, you can look in the text bubble in no ChatGPT, in Cloud or anything, and you can see what the model is thinking. But really, it's just autoregressive tokens. What I'm thinking is that what you could do is that you could output a prediction and then check the ground truth, then output another prediction to try and nudge like this and get a loss based on this. Sort of fine tuning, but I haven't really thought about I haven't thought how I can actually not cheat and show the ground truth properly and more incentivize iterating multiple prediction. One thing that I'm thinking about right now is that you could output maybe like 6 or 7 times the prediction and then compare it to the ground truth and do something related to GLPO. That's very similar to what GLPO is doing. So maybe that could work. If you output 10, 12, something like this of the outputs, and then you compare to the ground truth, that could be an interesting strategy. I think that would be something that could work, and that could be kind of analogous to what chain of thought is doing.
So, is there anybody online that would like to have a word or a question or comment?
No. How do I see the chat? Well, sharing control. Oh yeah, thank you very much. No, I don't think so. Unless someone is want to ask a question.
Just to congratulate with Hugo, because very impressive work.
Thank you very much. I appreciate it greatly. Anyone else? Any other question? All right, I'll take this as a no.
Okay, thank you. So, in that case, then I would ask the candidate and the general audience and also the general audience in the Teams meeting to.
I'm muting the mic. Thank you very much for attending the defense.